Hey, good morning, everybody. We are continuing lecture 2. You will learn now how to describe the soil model and the basic physical parameters. If you looked at a soil sample using a microscope, you would see the soil particles. Between them, you would see probably water and air filling the voids between the particles. Of course, the orientation of the particles would depend on the soil structure and on the type of the soil skeleton. Basically, this is quite a complicated material. So if you wanted to simulate its behavior, then you'd have to use quite sophisticated mathematical models, sophisticated software. Engineers usually tend to simplify life. That's why we will pretend that instead of such a complicated material, we have a material that we can describe using this very simple model. So we will imagine that we have all the solid phase like compacted together, all the liquid gathered here, and all the gas gathered here. If so, we can describe this model using its volumes and masses. So we will have the volume of the skeleton, Vs, the volume of water, Vw, and the volume of the gas, Vg. Volume of all the voids, so water and gas, will denote with Vv, V for void. And the whole volume of the sample will be Vt. Now on the right we've got masses. So mass of the skeleton, Ms, mass of the water, Mw, the gas will have no mass, so 0, and the total mass of the sample, which is the sum of the mass of the skeleton and the water, is Mt. Now using these masses and volumes, we can describe several physical parameters of soil. Okay, so let's start with the densities. In geotechnics, we are defining several types of densities. I hope that you know what density is. So it is a ratio of mass and volume. And in our soil model, the bulk density will be the ratio of the total mass and the total volume. So this equation here. Now some formal announcement. So the definitions in this presentation are always written as the first equation here, and bold font is used for that. So this is the definition of the bulk density. While these equations here can be useful for some practical calculations, but these are not the definitions, okay? The definition is the first one only. These calculations, these equations can be used, for instance, if you want to calculate the bulk density, but you only know the dry density and the water content. Okay, particle density. So the next definition is given here. So the particle density is simply the density of the soil skeleton. So it is the mass of the skeleton over the volume of the skeleton. As future engineers, you need to know the ranges of the basic parameters. So the bulk density for most of the soils will change from around 1.6 to around 2.2 tons per cubic meter, which means that if you assume that the soil density is around 2 tons per cubic meter, you will not be far from the truth. Now, let's look at the particle density values: 2.65, 2.65, 2.67, 2.72. You can notice that the range of values here is much smaller, and the particle densities of gravel and sand are the same, 2.65. And this is because the density of quartz is 2.65, and sand and gravel, in Poland at least, is usually made of quartz. So 2.65 is the density of quartz, and so this is the usually the density of the sand and gravel, but of course only of density of the soil skeleton. Another type of the density is the dry density, ρ-d. You know this density already from the Proctor compaction test, right? And the definition of that is the mass of the skeleton over the total volume of the sample. Unlike the other parameters, here I want you to remember also another formula, this one, which can be also expressed as this one. Okay, this is it is basically the same. So this formula, it is the same as this formula. The only difference is that if you express the water content in percent, you will have to use this formula. If you express the water content simply as a ratio, you will use this formula. From the Proctor compaction test, you already know that there are some soils for which it is possible to establish some maximum value of the dry density. But there are also some soils, they're called self-draining soils, where it is impossible. There is no one maximum dry density. However, for all soils, the dry density depends on the water content. It depends also on the soil type, and it depends on the energy of compaction. Water density, so the density of water simply, is the ratio of mass of water and volume of water. Usually we will assume that it equals 1 ton per cubic meter. But you have to remember that the water density depends on the temperature. So it is equal to around 1 if the temperature is close to 0. For other temperatures, it behaves like this, so like following this kind of parabola. Saturated density is defined with this formula. So it is the mass of the skeleton plus mass of the water, plus here we would like to add mass of the gas, but well, the gas doesn't have any weight, right? But instead of that, we are like, if there are any air bubbles in the soil, then they would have some volume. And now if the soil is fully saturated, then we have to imagine that even these air bubbles are filled with water. That's why we add this part here to the equation. The next parameter is weight. Weight, you can get weight if you multiply the density and gravity. Gravity G equals 9.81 meters over second squared. For engineering purposes, we can assume that it equals 10 meters over second squared, which means that if you are talking about the solid weight, then you would multiply the solid density by 10 and you shall get the solid weight. Okay. Here I think in this table the value 9.81 was used. Basically you see that it is simply like multiplied by around 10, so it's very simple to calculate the unit weight. What is very important is the unit. So the density is expressed in tons or kilograms per cubic meter, while the weight is expressed in kilonewtons per cubic meter. So it is the unit of force over the unit of volume. The weight is always used if you want to calculate the stresses in the soil mass. Another parameter connected with weight and density is the grain specific gravity. Specific gravity, GS. It is the ratio of the densities or unit weight of solids, so the soil skeleton, and water. So this is a unitless parameter. And in this table you see the basic values of the GS. So as I said before, for quartz you have the value of 2.65. Another minerals like K feldspar will have this value a bit smaller, biotite will have it a bit higher, and so on. So depending on the mineral composition of soil, the specific gravity and so also the particle density will be different. However, silicates, quartz is a type of silicate, so silicates are very common and account for about 80% of the minerals at the Earth's surface. So if you wanted to assume some value for the specific gravity, if you assume the value of 2.65, we will not be far from the truth. Another parameter that you have to remember is the water content. Again, the definition is written here. So this is the ratio of the mass of water in the sample and the mass of the skeleton of the sample. So it means the mass of the dried sample. Okay? The water content can be expressed as a ratio, then this is given as, for instance, 0.5 if the mass of water is like 50% of the mass of the skeleton, or it can be expressed in percent, but then you would multiply this formula by 100%. The natural water content of soil depends, of course, on the soil type. Because gravel, sands, silt, they cannot absorb much water. That's why the maximum natural water content will be usually less than 30. But if you are talking about clays, then here this natural water content may be much higher. For montmorillonitic clays, it can be much higher than 50. For organic soils, as you can see, the natural water content can reach even the value of 1500%. Water content of fully saturated soil, there is no definition, there are just formulae that can be used if you know some other parameters. But here we have the degree of saturation. We were talking already about that during the lecture 1. So it is the ratio of the volume of water in the volume of voids. The saturation ratio can range from 0 to 1 or 0 to 100%. Now, depending on the value of the S, the soil can be classified as dry, moist, wet, or saturated. According to the Polish standard, every non-cohesive soil below groundwater table can be assumed as saturated, and every soil wetted by capillary water, from which water doesn't flow out gravitationally, may be assumed moist without any special tests. So these are just some assumptions, some engineering assumptions that are sometimes useful. Now, void ratio and porosity. We have defined them already before. So just to remind, the void ratio is the ratio of volume of voids and the volume of the skeleton, while the porosity is the ratio of volume of voids and the total volume of the sample. So this is the difference between them. If you know the void ratio, you can easily calculate the porosity and vice versa, okay, using this formula. What are the values of the void ratios or porosities? If you imagine that the soil is built of uniform spheres, like here, then there exists an arrangement for which the voids between the grains will be the greatest. And there also exists some other arrangement where the voids will be the smallest. Okay, and based on some graphical simple calculations, we will know that the maximum void ratio for this type of material will be equal to 0.92 and the minimum 0.35. So the void ratio of such uniform spheres cannot be smaller than that and cannot be greater than that. For the porosity, it corresponds to 0.476, the maximum one, and the minimum one 0.958. These calculations were for some theoretical uniform spheres. Natural soils, of course, are not made of spheres. They have various shapes. But if you look at this table where the values of the void ratios and porosities are presented, then you can notice that for sands, the E-min and E-max values are not really far from these theoretical ones. So the theoretical ones are given here, right? While the other ones that you see here are the real ones. So, for instance, for sands, the minimum that you could find here is the 0.2 for fine to coarse sand in this table, and the maximum was like 1.2. Okay. But this is for sands, so for non-cohesive soils. Now, how does it look like for clays? Well, here you can look at this graph from the article by Scampton. What do we see here? On the horizontal axis, we have the effective vertical stress, which corresponds to the depth from which the sample was extracted. Pay attention to the fact that the scale here is a logarithmic scale. Yeah? On the vertical axis, we see the void ratio or the water content, W. They correspond to each other. We assume that, that the soil is fully saturated. If it is fully saturated, then the void ratio depends only on the water content and the relative density or specific gravity. Yeah. So let's first look at the samples here. These are the specimens that were taken from the bottom of the sea, and these are the results. Okay? The maximum void ratio that was noticed here, it is that point, you can see that it equals 4.5. So it means that the volume of the voids was 4.5 times higher than the volume of the skeleton. And the volume of voids is decreasing with the depth of the soil specimen, or it is decreasing with the effective stress that is applied on the specimen. It also depends on the liquid limit. See, this is the liquid limit, WL. The higher the liquid limit, the higher also is the void ratio. The samples that are shown here, so the ones taken from the just the bottom of the sea, bottom of the seabed, these are so-called normally consolidated soils. So they have never been loaded more than now, and they will always have the highest void ratios. Now, if you know the definitions of all the physical parameters of soil, then having values of one set of parameters, you will be able to calculate other values. For instance, known is the bulk density, the water content, and the particle density. And this is enough to calculate other parameters like dry density, porosity, void ratio, degree of saturation, saturated density, water content of fully saturated soil. Remember, for the exam and for the tests, I want you to know the definitions of all the physical parameters. And I want you to be able to reshape the formulae so that you can calculate one parameter using the other. In this example, which is solved here, I was using the ready equations, but I want you to be able to create your own equations. Okay, what is the solution here? Well, the dry density can be calculated with the formula that I was mentioning before. It equals 1.7 grams per cubic centimeter, porosity 0.359, void ratio 0.56. The degree of saturation will equal 0.6 around. The saturated density at the void ratio calculated before, so equal 0.56, will be equal to 2.058 grams per cubic centimeter, and the water content of the fully saturated soil at the same void ratio shall equal 21.1%. So all these parameters, all the values of all these parameters could be calculated if just three other were known. At home, I would like you to try to derive these formulae, because this is what I would expect you to present also during the exam.